Welcome back to Calculus 3. Today, we're going to talk about extrema. This will work somewhat similar to what we did in Calculus 1. If you're looking for the place where you have a local maximum at some point, you're looking for a place where maybe the tangent plane is horizontal, or perhaps where there is no well-defined tangent plane. You can see in the first case, you're looking for places where the directional derivative in every direction is 0. In the second case, you're looking for where the directional derivative does not exist at each point. The surface is not differentiable at this point here. First, let's define what we mean by a local maximum or a local minimum. We say that a function, perhaps of multiple variables, has a local maximum or a relative maximum at some place x naught if there exists a neighborhood Remember, a neighborhood of a point is an open set that contains that point in of x naught such that the height at x is less than or equal to the height at x naught for all x that lie in the neighborhood. So the height at x naught is the highest point amongst all of its neighbors in the neighborhood. A local minimum is defined in the obvious way just by reversing the direction of the inequality. Also, a surface can have more than one local maximum. You can have some neighborhood 1 here, where you have a highest point at some point x naught, and another neighborhood in 2, and some highest point in that neighborhood. If f is differentiable at x naught, and f has a local extremum, either a local maximum or a local minimum at x naught, then the gradient at x naught must be the 0 vector. This gives you an easy way to determine places to look for these extrema, at least if the function is differentiable. Both of the partial derivatives, partial derivative of f with respect to x, and the partial derivative of f with respect to y, must be 0. At the point in question. In higher dimensions, all the partial derivatives would have to be equal to 0. The proof is pretty simple. We'll choose two paths. First, path 1. This passes through the point x naught, which has coordinates x naught, y naught, at t equals x naught. Now, if f has a local max at the point x naught, then f composed with R1 has a local max at t equals x naught then, because that will pass through the point x naught at this value of the parameter t. But that means that 0 is going to be the derivative at t equals x naught of f of r1 of t, but that is, by the chain rule, derivative of f with respect to x times dx dt, derivative of f with respect to y times dy dt, evaluated at t equals x naught. But in this particular instance, dy dt is 0 because y is being held constant on this curve. Dx dt is going to be 1, and that means when we evaluate df dx at the point x naught, we must in fact get 0. Similarly, the derivative of f with respect to y at x naught equals 0, and that's equivalent then to the gradient being the 0 vector. This last theorem justifies the following definition. We say that x naught is a critical point, and these are actually points in the domain, unlike in calculus 1, of f if x naught is in the interior of the domain so there's enough space to put a neighborhood around it within the domain, and either 1, the gradient is the 0 vector, or 2, at least one of the partial derivatives does not exist. It follows immediately that if x naught is an interior point of the domain of f, and f has a local extremum at x naught, then x naught is a critical point. Of f. You should be careful to note that the converse is false. You can have a point where the slopes in all directions are 0, like on a saddle, but where you don't have a max or a min, maybe a max in one direction and a minimum in another direction on a saddle. So just because you're a critical point doesn't mean you're the location of a relative extremum, but we can limit the number of locations to look for relative extrema by finding the critical points. The only place to look for will be at these critical points. In our next example, suppose we have f of xy equals 2x squared plus y squared plus 8x minus 6y plus 20. If this is equal to z, what kind of surface is this? The only surfaces where we had z to the power 1 were either elliptic paraboloids or hyperbolic paraboloids or planes. Since we have squares, this is going to be some kind of paraboloid. Since the coefficients of x squared and y squared are both positive, This will be an elliptic paraboloid opening up. Now, we can find the critical point. There should be a unique critical point on an elliptic paraboloid opening up. Where is that critical point? So we'll calculate the partial derivatives and set them equal to 0. And that way, the gradient will be the 0 vector. When we take the derivative with respect to x, we get 4x plus 8. So it turns out x must in fact be minus 2. When we take the derivative with respect to y, we get 2y minus 6. In other words, y equals 3. So the only critical point is the point negative 2, 3. As another example, let's suppose we're raising this to the power 1/3. You might be able to graph this, and if you do, you'll see that the surface looks something like this. Where is that critical point? We'll take the partial derivatives and set them equal to 0. Taking the derivative with respect to x, we get minus 1/3 x squared plus y squared to the negative 2/3 times 2x, and minus 1/3 x squared plus y squared to the negative 2/3 times 2y. Now, you can see that we either have x equals 0 or the denominator 0. Remember, a negative exponent kicks the quantity into the denominator. That denominator is only going to be 0 when both x and y are 0. So when x is 0 and y is 0, we get both x and y is 0. Both of these partial derivatives are undefined at the point 0, 0. So this is, in fact, the unique critical point for this curve. Now for a slightly more complicated example, let's calculate the partial derivatives, set them equal to 0, and solve for x and y. First, fx. We have a product rule. In this case, there are only two factors that involve x. So we only have to do the product rule with respect to those other two factors. The other two factors are just coming along for the ride. Derivative of the first times the second plus the first times the derivative of the second. So we're getting y times y minus 2 times 2x minus 1. This gives you either x equals 1/2, y equals 0, or y equals 2. And these are or statements between here. We must also have the other partial derivative equal to 0. And here the x parts get factored out. Derivative of y is 1 times y minus 2 plus the first y times the derivative of the second. This gives us x times x minus 1 times 2y minus 2, or 2 times y minus 1. In this case, you get y is 1, or x is 0, or x is 1. What are the critical points? Well, we have to match these with these. So we either have x equals 1/2, y equals 1. That's the only, we can't attach x equals 1/2 to x equals 0 or x equals 1. So the only one that associates with x equals 1/2 is y equals 1. Though if you do have y equals 0, you can have x equals 0. Or you can have x equals 1. And if you have y equals 2, you can have x equals 0 and x equals 1. So far we have 5 critical points. Is that all? In the case where y equals 1, you can only have x equals a half. If you have x equals 0, you can have y equals 0 or y equals 2. And if you have x equals 1, you can have y equals 0 or y equals 2. You can see that we get 5 critical points for this surface. We would like to develop something like the second derivative test for relative extrema. To do this, I want to recall what we did in Calculus 1, but I want to approach it from a Calculus 2 sort of perspective. You'll recall that from Calculus 2, we have something called a Taylor series. And I'm going to write plus higher order terms, HOTS. Now, at a critical point where the function is differentiable, we can suppose that f prime at x naught is 0. So this term goes away. And if we ignore the higher order terms, then the curve looks much like a constant of vertical translation plus a quadratic, a parabola. If the second derivative is positive, then the parabola opens up, in which case you're dealing with a local min. If the second derivative is negative, you're opening down at a place where the slope is 0, which means you're at a local maximum. And that gives us the usual second derivative test from Calculus 1. So, parabola opening up, if second derivative is positive, you're concave up. That implies relative min. If the second derivative at x naught is negative, then relative max. It's that easy. Can we do something like this in the multivariable case? So in the multivariable case, what is the version of Taylor's theorem? We already know the first two terms because we've already determined the linearization. Yep, you take the value of the function and add the gradient evaluated at x naught. This will be a constant vector dotted with x minus x naught gives you a scalar. Scalar plus scalar is well defined. How do we do the next term? We're expecting 1 over 2 factorial, but we need something involving second order derivatives. How do you do the second order derivatives? Well, it turns out you have something called the Hessian evaluated at x naught times x minus x naught and then times x minus x naught plus higher order terms. Now, I need to explain what I mean by these dots here and here. It turns out the Hessian will be a matrix, and this multiplication will be regular matrix multiplication, whereas after you multiply the matrix times the vector, you get a vector. You're going to use the Euclidean dot product for the second product. So, what does this Hessian look like? Well, the Hessian is the matrix of second order partial derivatives. One way to think about the Hessian and I should spell that word for you, is that the first row is the gradient of the partial derivative of f with respect to x, and the second row is the gradient of the partial derivative of f with respect to y. So in other words, you calculate the gradient of each of the coordinates of the gradient. Now, let's look at the Hessian times x minus x naught times x minus x naught times 1 over 2 factorial, which is 1/2. We're going to have fxx, fxy, fyx, fy, y, and the coordinates of this will be x minus x naught, y minus y naught, and then we'll do the Euclidean dot product with x minus x naught, y minus y naught. When we perform this first matrix multiplication, we'll have fxx times x minus x naught plus fxy times y minus y naught. And then in the second row, we'll have fyx times x minus x naught plus fyy times y minus y naught. And now we're dotting this vector with x minus x naught, y minus y naught. This gives us 1/2 times. We'll multiply this coordinate times this coordinate. That gives us fxx times x minus x naught squared. I'm going to leave a little gap after the plus. fxy times y minus y naught times x minus x naught. But on the next row, we're going to get another one of those. Due to Clairaut's theorem, mixed second-order partials are equal. We will assume sufficient regularity that the mixed second-order partials will be the same. And then one more term, fyy times y minus y naught squared. Close parenthesis. Don't forget the factor of 1/2. And then to this term, we add the preceding terms and the terms afterwards, the higher order terms. So, for Taylor's theorem, I'll write out the first several terms that we have so far. We have f of x equals f of x naught plus df dx at x naught times x minus x naught plus df dy at x naught times y minus y naught plus 1/2 times fxx at x naught times x minus x naught squared plus twice fxy at x naught times x minus x naught y minus y naught plus fyy at x naught times y minus y naught quantity squared, close bracket, plus the higher order terms. We're going to assume that we are close enough to our critical point so that when we calculate y minus y naught cubed or x minus x naught cubed or any of those higher order terms, that those differences are so small that we may ignore the higher order terms. Also, keep in mind that at a critical point where you get differentiability, the gradient is the zero vector, so both of these terms will drop off. We'll assume that f is smooth enough to have continuous second order partials, so surely the first orders exist. And we'll also suppose that x naught is a critical point of f, and f is at least, we'll say, 3 times differentiable. The third order partials exist, so the higher order terms are going to be out there someplace. Then the gradient at x naught will be the zero vector, and we'll have the following. F of x will be equal to f of x naught, which is just a vertical translation, 1/2 times all of those second order terms. Now, if you ignore the higher order terms, you have squares on the x's and y's. You get what is called a quadric surface. Of which we have classified 6 different types. Now, what type of quadric surface do we have here? Because z is to the power 1, we may narrow this to one of 2 different possibilities. This is either an elliptic paraboloid, or it is a hyperbolic paraboloid. Ignoring the higher order terms, we have either an elliptic paraboloid or a hyperbolic paraboloid. And this will tell the entire tale. If it's a hyperbolic paraboloid, then you have a saddle, and it's going to be neither a max nor a min. If it's an elliptic paraboloid, what you get will depend upon if it opens up or if it opens down. But it should be either a local min or a local max. The question is, how do you tell which of these 3 cases you have? A proper analysis would require an investigation into what is called quadratic forms, which usually is investigated in a course on linear algebra towards the end. What we'll do now, though, is we'll look at some special cases and we'll try to generalize from that. Let's suppose that the mixed second-order partials are 0, just for now. If the mixed second-order partials are 0, then the kind of paraboloid that you get will depend upon the signs of only fxx and fyy. If these have opposite signs, you have a saddle point. If these have the same sign, then it's either an elliptic paraboloid opening up, at which point you have a relative min, or an elliptic paraboloid opening down. So it all comes down to a discriminant, which is fxx at x naught times fyy at x naught. We'll have, if d is negative, you'll have a hyperbolic paraboloid and hence a saddle. Saddle points have neither a max nor a min. If d is positive, then you have either a max or a min. It just takes a little more analysis to figure out which. In the case where d is positive, if one of the 2 factors is positive, then the other one must be 2. And that means the critical point can be classified as a min. If you're concave up in one direction, because the discriminant is positive, you'll be concave up in all directions, so that at the critical point, you'll have a local min. If, on the other hand, fxx at x naught is negative, that will imply you have a max. If you're concave down in one direction, you'll be concave down in all directions. So at the critical point, you'll have a local max. This is all nice and fine, but it only works if the mixed second-order partials are zero at the critical point in question. What if they're not? Then it depends upon something else. Remember that the Hessian is a matrix. It turns out that whether or not you have a local max or local min will depend upon the eigenvalues of the Hessian matrix. Now that's definitely a linear algebra topic. The true scoop goes like this. If all of the eigenvalues are positive, then you're concave up in all directions, in which case you have a local min. If all of the eigenvalues are negative, then you're concave down in all directions, and you're at a local max. If some of the eigenvalues are positive and some are negative, then you have a saddle point, and you have neither a max nor a min. If one of the eigenvalues is zero, then the test fails. Now, there is a theorem from linear algebra that says that the determinant of a matrix is equal to the product of the eigenvalues. Which means if in the 2 by 2 case, the determinant of this matrix, the Hessian, is going to be the product of the eigenvalues, and there's only two of them in the 2 by 2 case. That means if you get something negative, you have a saddle, because you'll have concavity being positive in one direction and negative in another. If it's greater than zero, that implies a max or a min, but to determine which, all you have to do is check concavity in one direction. Fxx at the critical point being positive implies you're concave up, so that you have a min. Fyy at x naught being negative, or xx, it doesn't matter which one you choose, implies you're concave down in one direction and hence in all directions, and so you have a max. So it all comes down to the determinant of the Hessian. Note that if you have more than two independent variables, the determinant won't be good enough. You could have two negative and one positive, it's still going to give you a positive. You won't be able to distinguish. So when it comes to more independent variables than two, you really do have to look at the eigenvalues of the Hessian matrix. In the two independent variable case, we can get away with just looking at the determinant. We'll have the following theorem. Suppose f is, let's say, really smooth in a neighborhood of a critical point x naught. Set d to be fxx at x naught, fyy at x naught, minus fxy squared at x naught. The determinant of a 2 by 2 matrix is product down the main diagonal minus the product the other way. And if you think about the Hessian for a moment, that will be exactly this, the determinant of the Hessian. If 1, the discriminant here is negative, then x naught is a saddle point, and neither a max nor a min. 2. If the discriminant is positive, we have two cases. A, if fxx at x naught is positive, that implies you have a local min. If fxx at x naught is negative, that implies you have a local max. And of course, if you get 0, then the test fails. And if the discriminant is 0, the test fails. So in our first example, let's look at minus x cubed plus 4xy minus 2y squared plus 11. To calculate the location of the critical points, we first have to set the partial derivatives equal to 0 and solve for x and y. We'll have what? 4x minus 4y. We end up with a system of equations. The second equation is a straight line, y equals x. The first equation is y equals 3/4 x squared. So, in looking for the critical points, we're looking for the intersection of a straight line through the origin and of a parabola with vertex at the origin. See, it stands to reason there should be two critical points here. Let's see if we can find both of them. If we substitute y equals x, we'll have x equals 3/4 x squared. We'll move this x over and multiply through by 4. You can now factor an x out and get x equals 0 or x equals 4/3. Since y equals x, we get the two critical points, 0, 0, and 4/3, 4/3. Now that we have these critical points, we need to find the discriminant. So let's find fxx. That's going to be minus 6x. Fyy will be minus 4. And fxy will be positive 4. The discriminant then will be 24x minus 4 squared, which is 16. We need to evaluate the discriminant at these critical points. At x equals 0, y equals 0, we get negative 16, which is negative. That implies we have a saddle point here. Evaluating this discriminant at 4/3, 4/3, let's see, 3 goes into 24 8 times 4 is 32, minus 16 is positive 16. That means we have either a max or a min, but it doesn't tell us which. To find out, we need to evaluate one of the second order partials, either fxx or fyy. Well, in this case, fyy is easier. Fyy, evaluated at our critical point and everywhere else, is negative 4, which is less than 0. Concave down in one direction implies concave down in all directions locally, and that means we have a relative max at the point 4/3, 4/3. By definition, a point is a saddle point if it's a critical point where you have points both above and below in some neighborhood. Now, what do we mean by absolute extrema? We say that f has an absolute max at x naught on the set S if the height at x naught is bigger than the height at x for all x within in the set. There's an obvious variation of this for absolute minimum just by reversing the order of the inequality. Do you remember the Extreme Value Theorem from Calculus 1? We're going to have a variant of that here. In Calculus 1, you were told that a continuous function defined on a closed and bounded interval attained both its absolute maximum and its absolute minimum on that interval. We're not working with intervals anymore. We're working with regions in the plane or higher dimensional regions. The extreme value theorem in the more general context goes like this. If f is continuous on a closed and bounded set, S. Remember what it means for a set to be closed? A set is closed if it contains all of its boundary points. Then f attains both its absolute max and absolute min on that set S. The critical characteristics of that set are it has to be bounded, which means you have to be able to draw a circle around it. It doesn't run off to infinity in any particular direction in the plane. And it must be closed. It has to have all of its boundary points. In particular, if I have a curved segment, that is a closed set, every point being a boundary point, and it's bounded because I can draw a circle around it. Now, if f is continuous on a closed and bounded set S, where are those extrema which must exist by the extreme value theorem? Where do they have to be? Then the absolute extrema of f on S must occur either at critical points of f or boundary points of the set S. We've seen already that the local extrema occur at interior points of the domain where the gradient is equal to 0, or the gradient has one coordinate or the other that does not exist, or both. However, the boundary points could also be locations of an absolute extremum. So we have to check not only the critical points, we have to check all around the boundary of whatever set we're dealing with. Let's look at an example. Let's look at the function sine of x times y. But let's restrict ourselves to the set x goes from 0 to pi, y goes from 0 to 1. We can write this as 0 is less than or equal to x is less than or equal to pi, and 0 is less than or equal to y is less than or equal to 1. Cross just means the set of ordered pairs where the first coordinate x comes from the first set and the second coordinate comes from the other set. Now, in the plane, we're looking at a rectangle. That set is bounded. You can certainly draw a circle around it. And it is closed. It contains all of its boundary points. The absolute extrema must either occur at critical points of this function or at some point on the boundary. By the way, I should tell you that the extreme value theorem is due to Weierstrass. One of the greatest mathematicians of the 19th century. He didn't really start to do mathematical research until he was at least 50 years old, but he was known to have been a very excellent teacher. We'll calculate the derivative with respect to x. By the chain rule, that gives us y times the cosine of xy. And then the partial derivative with respect to y, which gives us x times the cosine of xy, x times y. Now, by the zero product theorem, the zero product theorem says that if a times b is 0, that's true if and only if a is 0 or b is 0 or both. So we have y equals 0 or cosine of xy 0. And we also have x equals 0 or cosine of xy is 0. So 0, 0, x equals 0, y equals 0 is a critical point. If x is equal to 0, cosine of 0 is 1, not 0, so you would have to have y equals 0. The only other critical points are those where cosine of x times y is 0. Well, where does cosine x times y equal 0? That only happens when x times y is pi over 2 plus n pi, where n is an element of the set of integers. Anytime I have xy equals a constant, I get y as a constant divided by x, and that gives me a hyperbola. In fact, you can kind of see this from the old formula b squared minus 4ac from pre-calculus, where b is the coefficient of the xy term, a is the coefficient of x squared, and c is the coefficient of y squared. Both of those are 0 here. Since we have a coefficient of 1, that's positive. Whenever you get a positive on this discriminant, you end up with a hyperbola. If you get equality with 0, it's a parabola. And if it's less than 0, it's an ellipse. But not all of these hyperbolas intersect our region. In particular, if n is equal to -1, then c is going to be negative. And if c is negative, whenever x is positive, y will be negative. X positive, y negative, that puts you in quadrant 4. Our region is in quadrant 1. So you can assume that n can't be negative. Can we have n values bigger than 1, though? What if n is equal to 1? If n is equal to 1, we have xy equals 3 pi over 2. X only goes up to pi. If x goes up to pi, in order to get to 3 pi over 2, y would have to be 3/2. This hyperbola never gets down to our region, which means that even n equals 1, the hyperbolas don't intersect the region. What if n is equal to 0? That's the only other case that can possibly intersect our region. If n is equal to 0, we get x times y equals pi over 2. And if x is equal to pi now, the right-hand endpoint of our region, y is going to be 1/2. We will in fact have intersection between this hyperbola and our region, but this is the only case. The critical points then are either 0, 0, or points xy equals pi over 2 that intersect this rectangle. Just on this little segment here. We could ignore everything else. And our region of definition is everywhere in here. we said that we intersect at 1/2 here, but if x is equal to halfway across, pi over 2, y must be 1. So we intersect the top part of the region at x equals pi over 2, y equals 1. So those are our critical points. Now, to find the absolute extrema, we have to evaluate the original function at the critical points and also the boundary points. But there is one other thing to keep in mind. X times y gets up to pi over 2, but it can't get bigger, which means that the argument of the sine function is between 0 and pi over 2, quadrant 1. Sine of x is between 0 and 1 for x values between 0 and pi over 2. So 1 is going to be the potential absolute maximum, 0 the potential absolute minimum. You can't get anything lower as long as xy is between 0 and pi over 2. When we plug all points of the form xy equals pi over 2 into our function, we get the sine of pi over 2, which is 1, and that has to be the absolute maximum because that's as big as sine gets. When we plot the point 0, 0, again, we get the sine of 0, and that's 0. That has to be our absolute minimum on this region. Well, are there other places that are also absolute minima and absolute maxima? We have to check the boundary points. So we have 0 here and 1 along here. Let's define the boundary of S1 to be the places where y equals 0 and x goes between 0 and pi. On all of these places, y is equal to 0. Which gives us 0. Those are the places all the way along this boundary, this piece of boundary. All along that piece of boundary, we get the absolute min of 0. Let's talk about this boundary then. That's where x is equal to 0. We'll call that boundary of S2. And again, f of 0y is the sine of 0, which is 0, and that gives you the absolute min. Again, all the way along this side, we have 0. What happens on this right boundary? Let's call that boundary of S3. All along that boundary, x is equal to pi, and y goes from 0 to 1. If we evaluate at those points, we get the sine of pi y, period being 2 pi divided by pi, which is 2. Since we're only going from 0 to 1 on the y, and the period is 2, there should be a max halfway across at 1/2. In fact, there is. You get a height of 1 here, but by the time we get to 1, we should be back down at a minimum, both at 0 and at 1. So at this endpoint right here, we get a height of 0, and that's an absolute min. We have one more piece of boundary to check. Let's look at boundary of S part 4. I should mention that we have this one notation that looks like a partial derivative symbol, but it has two distinct meanings, and you'll have to interpret it based on the context. When we apply this notation to a set, we're talking about the boundary of the set. When we apply it to a function, we're talking about partial derivatives. Let's look at the points where the y-coordinates are all 1, and the x-coordinates are between 0 and pi. When we evaluate our function on these points, we get the sine of x, which has period 2 pi, like normal. We're only going as x goes from 0 to pi, so we'll reach this maximum at 1/2 pi, and at 0 and pi, we'll have values of 0. So we get nothing particularly new here, just another re-emphasis that this point at the right-hand upper right corner gives us an absolute min of 0. So you can see we had to check this function not only at critical points, of which we had points along this curve all being critical points, and the lower left corner of the rectangle being a critical point. That was insufficient. We had to check all of the points on the boundary as well. By doing so, we picked up two whole boundary edges as being absolute extrema, and the upper right edge also an absolute extremum. Sometimes this discriminant for the second derivative test in the multivariable case fails us, but that doesn't mean all hope is lost. I want to give you an example. Suppose f of xy equals x squared y squared. Let's find the critical points. We'll have 2x times y squared equal to 0. So you get x equals 0 or y equals 0 by the zero product theorem. Here you'll have 2x squared y, which again means x equals 0 or y equals 0. There's an and statement between these. At the points where x equals 0, that's on the y-axis. Every point on the y-axis is a critical point because that will satisfy both of these requirements. Every point on the x-axis is where y is equal to 0. And so those two will all be critical points, as will, of course, x equals 0, y equals 0. Every single point on the x and y-axis is a critical point. So, how does that help us figure out the extrema of this function? Note that this function can't be negative because it's the product of two non-negative things. The lowest it can get is 0, and it achieves that absolute min of 0 on the x and the y axes. So at each point on those axes, you do in fact achieve the absolute minimum for this function, a value of 0.
I should show you a plot of this surface that we have been investigating. Let's write with plots, and f is defined to be the function that maps x comma y into the sine of x times y. And I want to plot 3D f of x comma y. X goes from 0 to pi, y goes from 0 to 1. Oops. Oops. Let me go up and semicolon. And there is our piece of surface. You can see where the coordinate axes are. We have our absolute minimum on these two lower boundaries along the x-axis and on the y-axis. We have this ridge in the shape of a piece of that hyperbola where we have that height of 1 all along that ridge. It's a constant height of 1 all the way along that ridge there, and then it comes back down to 0 at that lower right corner. So you can see what this looks like as a piece of surface.